Okay, so it's a time for the session 8. Topic is about ARX. And this session has 3 talks. Oh, Kai is ready? Okay. 1 minute. Okay. Okay, so that we can start. The first talk is perfect monomial prediction for modular addition by Kai-Fu and Trevor Yap. And Kai-Fu presents the talk, please.
Thanks for the introduction. My name is Kai Hu, and this is a joint work with Trevor Yap, and the title is the Perfect Monomial Prediction for Modular Addition. So let me give some background knowledge about ARX suffers. So ARX suffers are designed with modular addition, rotation, and XOR. And the modular addition is usually the only nonlinear operation. And there are already many famous ARX suffers, such like spike family and RZ S-box. Next are the integral attacks and the divariant properties. So the integral attack is to study the sum of some subtext bits or a linear combination of these bits under some structure, is 0 or 1 or some constant. And currently, divariant property is the best way to detect integral distinguishers. Divariant property was proposed by Yosuke Todo 10 years ago. So in the past 10 years, there are lots of variants of divariant property. For example, the original 2 subset and 3 subset divariant properties, and also the parity set, the 3 subset divariant property without unknown subsets, monomial prediction, and algebraic translation matrix. All these variants follows a similar framework. That is to say, we decompose a suffer into many small functions. And for each function, we can develop some propagation rules. And according to these rules, we can get some trials. And these trials can be handled by some automatic search tools, such as MIOP, just like the differential characteristics. So when applying divariant property to ARX suffers, firstly, we need to see how or what kind of components inside the suffer. For example, in this example, this is a one round of RZ. So there is a modular addition here. So then we need to give the input variable and output variable some constraints to force them follow the propagation rules. And in this paper, our target is to develop some perfect propagation rules for divariant property for the modular addition. Before our paper, there are actually already 2 divariant property models for modular addition. The first model was developed by Sun, Wang, and Asia Crypto 2017. So they decompose a modular addition operation into 3 basic operations, that copies, and XORs, because any vector Boolean function can be written in these 3 basic operations. Then you model these basic operations following their propagation rules. Another method is was proposed by Bier, etc. at Crypto 2020. So the authors also decompose modular addition into a sequence of small S boxes considering carry bits. For example, for this, we regard this as a S box with a 3-bit as input. So X is the left branch and the Y is the right branch, and the C is the carry bit calculated by the previous calculations. And also the output is another carry bit, and also the real output of the modular addition. Then because this is a 3-bit input and a 2-bit output S box, it's very small, so we can also apply the propagation rules for the S box to these small functions. Then connecting them together, we can get the whole propagation rules for the whole modular addition. However, the first model is obvious too complex. You need to memorize a lot of sequence of operations. The second model is simpler, but both models were proposed for the two-subset division property. The two-subset division property was is an imprecise model. That means even for a small operation, it will bring some redundant trials. So it will bring some impression, but of course it is faster and more efficient. So the motivation of our paper is to give a simple and precise division property model for modular addition. Our tool is monomial prediction. The monomial prediction is a precise version of a division property. It's same to 3-subset division property without unknown subsets, and also similar to the parity set and algebraic transition matrix, but from a slightly different viewpoint. Okay, according to this notion, for a vector Boolean function, we first assign some variables for the input and some variables for the output. So if the input variable can propagate to the output variable, then this monomial should appear in the output monomial. Because y is a function of x, so if you write y to weigh this monomial into a polynomial of the x, then you can get lots of monomials. Then you can check if xu appears in this set. So according to these propagation rules, and we apply this propagation rule to each of the components, and then we can get a so-called monomial trial or division trial. So a central proposition of this method is that if the original monomial can appear in the final in the output monomial, then the number of monomial trials connecting the input monomial and the output monomial must be an odd number. So it's a 1 mod 2. So to study the monomial prediction for modular addition, we need to study the rules for u, v, and w that make xu, yv, this monomial appears in the zw monomial. So it's equivalent to say we need to study the algebraic structure of the modular addition. So it's a bit surprising that there is already a theorem from Bracken and Simon and FSE 2005. So in this theorem, they said if xu, yv, this term appears in zw, this monomial, then u plus v should be w. Here the plus is the addition for integer. So from this theorem, it directly leads to the perfect propagation rules for the division property. Here I say it's surprising because this paper was published on FSE. So some symmetric guy, people should know it. And the division property is so popular, but in the past 10 years, no people had used it for modular addition. However, we find that in their paper, the theorem was proved in an involved way. They used 2 lemmas and a complicated proof. So with monomial prediction, actually we can have a very simple proof. So firstly, we also decompose the modular addition into such a sequence of small functions. And then we only need to prove that given any input monomial and output monomial, there is at most 1 monomial trial that can connect the input and output. So either there is no monomial trial, either there is only 1. And the second is based on some observations. You can find it's exactly in the addition for integer. So first, we assign the division property variables for the input and output for each small s box. Small s box. Then we can construct the division property propagation table for this small s box. And it's very interesting to see that from every input, there is only one possibility for the output. That means when you connect them together, there is at most only one trial. Because there is only one output, so it's actually a function, so we can write out its NF. When you write out its NF, you will find it's just the addition, but in the bit-based level. But I'm not sure if it happens to be like this, or there are some unknown algebraic structure to force them like this. So with these propagation rules, we can very easily develop some model for tools. The first model we provide is the SMT model, because MST server support directly the addition. So you can write it in a direct way. The following two constraints is to provide some protection against the overflow, because it's the addition for integer rather than a modular addition. The second model is a bit-based model, because currently the bit-based search model is more popular. So in this model, we just transform the addition into bit operations. So for each bit, we only need one equation for it. And also the L0 is 0 and Ln is 0 is to make it addition rather than a modular addition. Okay, next are some applications. The first application is about some new distinguishers for spec. Here are only results for spec 32 and spec 48. The results for remaining spec variants are in our paper. So the time one is the time the model cost in previous papers. So the most recent results is this one. So they found a distinguisher with 1 hour. Here they found that in the propagation, there is 1 bit of key involved into the propagation. So here I have a column called key marks. The key marks is just to sum up all the key variables, and then we for example, to calculate its maximum value. So because it's 1, that means at most only 1 bit of k is involved. Here, the 3 means at most 3 bits are involved. Because the k max is not so large, that implies that the super poly of this structure is not too complicated. So we can just count the number of trials using our models. So for this case, there are only 2,570 trials, so it can be searched out without 1 second. And the second case has more trials, but it can also be finished in 13 seconds. Also for spec 48 and other variants, there are similar results. For spec 128, it costs more time, maybe several hours or 1 day. Yeah, but it's still efficient. This is also beneficial to say that we can just try the consistent way to count the number of trials to find some distinguishers rather than to develop some other complicated propagation rules. But of course, if counting the trials are impossible, then you can consider to develop some new trials, new propagation rules. The second application is about calculating the algebraic degree for spec and R-zeta. For spec, because it's a k-ed cipher, so actually the degree here is the greatest algebraic degree. That means you can find some k value to make such term exist. So we find that all the 7 round spec 32 outputs, the 31 degree terms already appear. And for the R-zeta, we proved the exact algebraic degrees for all bits, 16 bits, 2 bits, for 2 round, 3 round, and 4 round R-zeta output bits, respectively. And for 4 round R-zeta, 31st and 47th bit are 63 degrees. This result is interesting because the designers of RZ actually wanted to provide some evidence that the algebraic degree of RZ is enough, but they have to do some experiments. So the lower bound is only 32, but here we can give some theoretical exact algebraic degree. So I think it will be useful in the future design. But of course, there are also some limitations with this method. Firstly, it does not work for spec 48 and other larger variants. And even for spec 32, we failed to provide the integral resistance. The integral resistance is to say that for any linear combination of the outputs, and considering any combination of the input structure, there is no integral distinguishers, but we failed to provide such a strong resistance guarantee. And also for RZ, we can only work for the 31st bit and the 47th bit, two weakest bit. But for other bits, we cannot do it. The third result is we slightly improved the Sparkle integral distinguishers. So you can see the data complexity is saved by half. We also applied our model to some ciphers which has been checked with previous models, but we didn't find any new results for LEA, height, and SHA-2. So the last application is a discussion on the rotation constant choice for spec family. So it is well known that spec designers did not give sufficient rationales for their choices of rotation constants in their original paper. Although later they gave some reasons for their choices, but they focused on the differential and linear attacks. Of course, differential linear attacks are the most threatening attacks for ciphers like spec. But here we still want to give some criteria for the resistance against the integral attacks. The criteria we choose is the max K. So just as I said, we just sum up all the K bits and to calculate the maximum of the such value. If this value is very small, that implies the superpoly is very simple. And if this value is very large, that means the superpoly is very likely to be very complicated. So to counting the number of trials is very difficult. Of course, there are for n-bit cipher, we have n possibilities for the input monomial. So we should use the minimum of the mask K, considering all the input cases. So for some alpha and beta choices is shown in this table. So with this larger minimum of max K, we indeed can do something better than the previous than the original parameters. For example, we can prove that all 6 round spec 32 output bits already have all 31 degree terms. This is also the same with the spec 48 and spec 64. So recall that with the original parameters, we can only do it for spec 32 with 7 rounds. Okay, so in this paper, we provide 4 parts of contributions. Firstly, we give a perfect division property propagation rule for modular addition. With this propagation rule, it is precise, and you do not need to memorize a very complicated formula. And we also for the algebraic degree for spec and RZ, we also conducted a discussion on the choice of rotation constants of spec family. Okay, that's all, and thank you for your attention.
Thank you very much for talk. So from the audience, is there any question? Yeah.
Thank you for the nice talk. I was wondering, so in the proof of this property, you use monomial trails, and you show that there is basically only one. Does that mean that the original model by Sun, Wang, and Wang is equally, like, I mean, gives you the same propagation rules, but that this is more efficient, or do you actually like cancel out some trails that did happen in Sun, Wang, and Wang's model?
Okay, so you can see for each small functions, there is only one monomial trial that is possible. So there is no redundant trials. That means the model will be precise. At least for this modular addition, the imprecise is actually brought by the copy operation.
Yeah.
But for efficiency, actually in our paper, we used some techniques to divide the search into many small cases. I think that's also the resource of the efficiency. Because with the previous models, for example, this one, although it's very complex, but if you run the experiment, you will find that actually it's also very efficient. But if you want to find some complicated distinguishers, for example, this one, before our paper, there is only one paper that can detect this distinguisher. But in that paper, they need a new propagation rules for the KXOR to cancel the affection of the k bits. And their model, you can say it's used 1 hour and 3 hours for spec 48, but with counting the trials, it's very quick.
Thank you.
Yeah. Thank you.
Thank you very much. So is there another question? So can I have one question?
Sure.
So please go back one slide. Yes, so sorry,
sorry.
here. So you have two models, so the bit-based model and the SMD model. So the which model did you use for the experiment?
The second one.
Yes, second one.
Yes.
Okay, so why you don't use the first one?
Oh, okay. So I think when you it provides the addition directly. But the problem is for other operations, the copy and XOR, they are bit-based. So you still need to do the transformation.
Okay.
Yeah.
So actually, I also think that actually in this case, the MIRP is also very familiar, but there's the same reason. So you don't think MIRP is better to model.
You mean model the integer?
Yeah, MIRP, so we can support integer additions
Yes.
so easily.
But I think it's similar because you also need to transform the integer to bits for other operations.
Okay, I see. Okay, thank you very much.
Thank you very much.
Okay, so thank you, Kai.